Okay. Good evening, students. So today, actually, I am going to show you the instruction from the branch and machine control group. Okay. So what we have in the instructions in the branch and machine control group are like jump instruction, JMP, jump conditional instruction means jump with different kind of conditions, with carry, without carry, with so if I click on this it will be clear. So NJ jump on 0, non-zero jump on 0, jump on no carry, jump on carry, jump on parity event, jump on parity order. Okay, so these are the flag conditions that we can use with jump instruction. Okay, so here we have jump instruction also. In the jump instruction, you don't need to use any conditions there. Okay, but in jump conditionally, here there you have to use some conditions. So these are the jump instruction, and what is the use of jump instruction? Is just to check the condition and then jump accordingly. That is the jump with condition. And if you just use simple jump unconditional instruction, that is JMP, then that will only be used for just simply jumping from one location of your program to another location. Okay, so jump JMP is used to jump from one location of your program to another location, and jump conditional will be used to jump from one location of your program to another location depending upon some given conditions. So this is the jump instruction, and then there is call instruction, call unconditionally and call conditionally. Okay, so what is that? So call instruction is called unconditionally. CALL call unconditionally. So here you can call a subroutine. Whenever you invoke this instruction in your program, it will be used to call a subroutine. So what is subroutine? Subroutine means suppose you have to do some specific task in your main program. You can write, instead of writing that thing in your main program, you can write that thing separately. Okay, so that as it is a very important task, so you are writing it separately so that there will be no error while writing this task. Okay, that is the one use of writing a subroutine. Or you can, if you are writing a lengthy program where you are actually writing many a times a particular set of instructions, instead of writing particular set of instructions, say 10 set of instruction you are writing repeatedly in your main program. Instead of writing repeatedly in your main program those instructions, you can write those instructions separately in a subroutine and call that subroutine whenever it is required to execute from your main program. So this way, if you separate those 10 lines from your main program to subroutine, what actually is the gain of your program? First of all, it will reduce the size of your main program, and second thing that it will be more easy to understand by the programmer and any other user what is going on in your program. Okay, so that is the use of call instructions. And you can also call your subroutine using call on different conditions like this: call on non-zero, call on zero, call on no carry, call on carry, call on parity event, call on parity on. So these are the conditions by which you can invoke these instructions depending upon different conditions of your flag. So these are all flags. So flag conditions, it is written depending upon flag condition. You can also use call on carry, call on no carry, call on zero, call on no zero, call on parity event, call on parity, or these are this type of instruction in your main program. Okay, so this is the use of call instruction. You can call your subroutine using depending upon the different conditions of flag, or unconditionally you can also call your subroutine. But whenever you are actually calling a subroutine, at that time you have to remember in that subroutine you have to remember that in that subroutine you need to use the return instruction Okay, this return instruction you need to use there. Why? Because you are actually transferring the main program to your subroutine. So once the subroutine, all the instructions of that subroutine program are executed, it should return back to your main program. So for that reason, you have to use RET instruction at the end of your subroutine, so that your program will come back to your main program from the set of subroutine program. That is the use of RET instruction. So RET instruction is actually return instruction. It is used for returning from the subroutine to main program. You can return with different conditions, or you can return unconditionally. So it is better to use unconditional return, because you have to have return from your subroutine to main program. So in that case, you need to use RET instruction. There you cannot use this return with conditional instructions. Okay, return with conditional instruction will affect in different set of programming types, but here in normally what we are doing, we are just calling a subroutine, execute some lines of code, then return to the main program. Okay, because returning to the main program is mandatory one from your subroutine. Okay, so that is the operation that we can do using return instruction. So jump, call, return, these are the very important instruction while writing a long lengthy program with different complex logic. Okay, because you have to use different kind of jump, call or return instruction. Okay, and there you can see that push and pop, these two instruction basically used whenever you are using stack memory. So stack memory actually, what is stack memory actually? Do you have any idea what is actually stack memory? Can you tell me? I hope you got some idea about the stack memory, because I have spoken many things related to stack in our theory class. So stack memory actually used during program execution. Okay, and it is totally the use of stack memory is totally depends upon the programmer, right? So suppose you are the programmer, you want to use stack for different purpose. So what is the main purpose of using stack? So the main purpose of using stack is to store those data, crucial data, very importantly. And hear this thing very, give your attention to this particular sentence that I am going to say, that stack memory is used to hold very important and crucial data of your program. Okay, why I'm saying this thing? Because whenever you are actually inserting this call instruction in your program, at that time your stack memory is used. Okay, why stack memory is used? Because you have to return back from your main program, you have to return back from your subroutine to main program. So how you will return back if you don't know at which address where you have to return back? Okay, so returning back means return to particular address location. So which address location will return back? That address location, 8085 simulate in 8085 processor will store into the stack memory. Okay, so that is why stack memory is important. So whenever you will use the call instruction in your program, at that time 8085 when execute that instruction, 8085 will use stack memory to push the 16-bit address into that stack memory. Okay, so that from the subroutine when you are coming back to your main program, so that you will understand what actually microprocessor will do. Microprocessor will at that time, when returning time, it will take that 16-bit address from the stack memory and return to the main memory address. So that is the address of main memory. So I will give you the example so that these things will be clearly understood by yourself. Okay, so basically here I have written a small code with all these examples of jump conditional, call instruction, return instruction, push and pop instruction. So these are the instructions which are used in the branching and machine control group. Okay, So actually what I am doing, I am I am initializing my stack pointer. This is the very much essential thing that you need to do. Initialization of your stack pointer, because in this particular program I am going to use stack. Okay, so if you want to use stack, then you have to define the stack pointer. Otherwise, the default value of stack pointer, you know what is the default value of stack pointer? Whenever you execute your program, the default value of your stack pointer is, you can see here, 000. So 8085 processor will take this as a default value of your stack pointer. Okay, so you can, so what actually you can do, you can define your stack pointer so that you will understand that what is the stack pointer value. Okay, so it is better to define a stack pointer value. So here I have defined the stack pointer as FFFF. So this is the location, starting location of your stack pointer. Okay, this is the starting location of your stack pointer, and you know that concept. In that location, there will be no data. There will no data will be pushed. In this location, there no data will be pushed. Actually, why? This is the way of stack is handled. Okay, so stack pointer, this is, I am, what I am doing, I am giving a 16-bit data into stack pointer register. I am not using the stack memory. Using the stack memory and initialization of stack pointer register is totally different thing. Here I have not used anything related to external memory. It is just an initialization of a register which is there internally in 8085 processor. That is the stack pointer. Then what I am doing, I'm moving a data into accumulator. I am adding data, another data with the accumulator. Okay, just the addition. Then depending upon the condition of carry, depending upon the status of your carry flag, I am taking the decision. If there is no carry, then my program will jump to L1 location. Okay, here you can see L1 location. If there is no carry, then my program will jump to L1 location. So why I am using JNC after ADI? Because after addition, arithmetic operation, all flags will change. So there is a chance of getting carry or not getting carry. So according to that, I am taking here the decision. If there is no carry, then it will jump to this location L1. Okay, and what it will do in that location? In that location, I am calling a subroutine 1. Okay, so here you can see I'm calling a subroutine 1 S1. So I'm calling a subroutine 1 S1. So program will go to this location S1 location, because I'm calling this. So what I am doing there, I am just initializing HL register pair 5555. Okay, and after initializing HL register pair, I am pushing that pair into the stack using push instruction. Okay, so I am inserting that data into the stack using push instruction, and then I am returning back from my stack. Sorry, from my subroutine. I am returning back from my subroutine to main program. Okay, so the RET, I have to write this RET instruction here. So RET instruction will return to which location? It will return to a particular location. So what, in which location it will return? It will return. So you have called this, from this instruction you have called this subroutine 1 from, particularly from this line of code. Okay, and then which is the next instruction? This is the next instruction. So return, actually this return instruction actually, return instruction actually return from the subroutine to the this instruction address. Okay, so this is the next instruction that needs to be executed. So it will return to this next instruction that needs to be executed location. So this is the location where it will return HLT. So it will execute this instruction, end of your program. So this is the way this program execute if there is no carry. So what this program is doing, if there is no carry after addition, it will actually calling a subroutine 1. There it is doing some operation, then coming back to the main program, and then it is ending here. Okay, and then here also I am going to show you, if there is carry, then what happens? If there is carry, then it will, this line will not execute it completely. Remember what I am saying, very important terms. This instruction will not be executed completely. Why I'm saying not completely execution? Because in complete execution, this instruction will take actually, it will take actually three machine three bytes of size, and it will take three machine cycles, opcode fetch, memory read and memory read, and it will take 4 plus 3 plus 3 10 t state. That is the case for complete execution of this instruction. But when there is carry, this instruction JNCL1 will not be executed completely. That means it will take only two machine cycles, but it will take 3 bytes, and it will take 70 state 4 plus 3. Okay, because why it is taking one less machine cycle? Because here there is a carry. So as the carry is there, so this line of code will not be completely executed, because if there is no, not it is not necessary to execute complete line, it is not necessary to jump on this location L1, right? That's why this instruction will not be completely executed if there is a carry. Okay, so how many machine cycles taking when there is a carry? Two machine cycle. Why two? Because why not it is one taking only one machine cycle? Because the first machine cycle is opcode fetch, that will be taken by this instruction. Okay, and when it will actually microprocessor is doing opcode fetch of this instruction, it is not possible by the microprocessor to check the status of your carry flag. So after opcode fetch, when this instruction goes to the next machine cycle, that is the next memory read machine cycle, there during memory read operation, the back of the side, the status of your carry flag is also checked. So there, after checking the status of your carry flag by the processor understands that carry flag value is 1. So this line of code is not required to execute completely. So it will just stop the execution of this instruction there. So that means what? Opcode fetch and memory read. These two machine cycles are there only. Okay, so two machine cycles, 70 state, but 3 byte size it is taking. Okay, if it is not completely executed, but also it is taking 3 byte of size, because 3 byte of size is not actually something which is depends upon any condition of your carry. It is the size, 3 byte size is for loading this data into the memory location. Okay, so this 3 byte will be there. So this is the done for this. So there is a carry, so it will not jump to L1, it will go to the next in the instruction, that is calling of subroutine 2. So it will call the second subroutine, that is S2. In the S2, what it is doing, it is taking out the data. It is taking out the data from the stack. Where it is taking out the data? In the BC register pair. Okay. So in the BC register pair, it will take out the data from the stack, then it will return to the main program. So in which location it will return? It will return to the next instruction that needs to be executed, that is JMP end. That is JMP end. Okay. Then what happened? So JMP end means what? Now JMP means this is the unconditional jump. So program returns from the second subroutine to JMP end location. There it is written that unconditional jump to which label? End label. So in the end label it is written halt. So end of the program. So program ends there. Okay. So that is the program. So here you can see in this program you have used call instruction, call unconditional call instruction, unconditional return instruction, conditional jump instruction, unconditional jump instruction. Okay. So this is the program what we are I have shown here for to understand all this instruction operation. Okay. Now then you can do the experiments by your own. Now if I execute this program, so let me just take these locations. Why I have taken this location? Can you guess why I have taken this location here? Because you see that these are the locations I have taken from triple F A B C D E F, because these are the location of your stack. Because your stack, you have started your stack from the FFFF. So I should not write FFFF first, then go to the next location. After FFFF, what is the next location? Address. Can you tell me? In 8085, we have 16-bit address bus. So using 16-bit address bus, the maximum number that we can enter, that is FFFF. So after that, there physically there is no location is available in your memory in your external memory chip. Okay, so basically I have used for that purpose FFFF is the last location for your stack pointer, and then I have decreased these locations. This is the last location. If it is the last location, then you cannot go beyond this. So basically, where you have to go, you have to go FFF E D C like this. You have to decrease this location. And also this is the thing that you need to do whenever you are working with the stack memory, right? Stack memory, because stack memory is handled in a different way of your normal memory handling process. In normal memory handling process, if you want to insert a data, so first location, suppose you insert a data into this location, so FFFA, so you have insert one data here. If you want to insert the next data, you can insert manually into the previous location of this FFA, FFF9. Into that location, you can insert the data manually. But normally, what happened if you just consider that processor is pushing the data continuously into the memory location, then it will go to the next location. Normally, that is happening in all these RAM, ROM cells, right? It will increase the next, it will go to the next location, insert the next data, go to the next location, insert the next data. So whenever you are handling the main memory, normal memory, you when you are inserting the data, the address is increased, FFFF A to B, then C. This way it will increase and data will be inserted. But in the stack memory, it is reverse. That means when data is inserted, your location address will be decreased. Okay, so initially it is located at this location. When the data will be inserted, location will be decreased and data will be inserted. Location will be decreased, data will be inserted. Okay, and also one another important thing, that whenever data is inserted into the stack, it is in this environment, it is not possible to insert only 8-bit data at a time. You have to insert a 16-bit data. PUSH, push instruction, will insert a register pair content into the stack. That means it will insert a 16-bit data into the stack. It is not inserting 8-bit data. POPB, pop instruction, pop B. So it will pop out 16-bit data into BC register pair. It is not actually pop out the 8-bit data into a one register. It is not pop out the data of one location into register B. It is actually popping out the two data from two locations into register B and C, BC register pair. So that is the thing you need to remember. So this is also a different thing with respect to normal memory of operation. In normal memory operation, we can insert 8-bit data or you can insert 16-bit data. Okay, but in stack memory, you cannot insert or take out 8-bit data at a time. You have to take out 16-bit data at a time, or you have to insert 16-bit data at a time. Okay, so here you have to use register pair for inserting or taking out the data from the stack memory. And stack memory and stack pointer register are totally different thing. Stack pointer register, this is the SP. What is the function of SP? SP function is to locate the top of the stack location. What is the top location? What is the top location address of your stack memory? That will be there in SP register. So that will be there in SP register automatically. You don't need to do it. What you are doing here, actually, you are specifying this address in the stack pointer, but you have not do anything here in this code. You have you done anything related to stack pointer in this throughout this code offline? No. So that does not mean that the stack pointer value will be FFFF always be like this. It is not a constant value. You will see here that initially this stack pointer register value will be FFFF, but it will change according to the operation. You will see that. So that means who is actually changing the stack pointer register value? The processor. You are not changing. You just initialize the stack pointer, and rest of the operation related to stack pointer register are done by the processor itself. Okay, so stack pointer is actually, what is the function of stack pointer register? To locate the top of the stack location. So stack pointer register actually holds the address of the stack, top of the stack memory location. So if you are initializing this thing with FFFF, so that means you are initializing that this is the top location of your stack. Okay, so like that. Okay, so let me just execute this program first, so you will understand everything. The first line I execute, so my stack pointer value is now FFFF. Okay, second line will be executed, so accumulator value is now F2. Third line is executed, addition is done. So 23 F2. So what is there? There is carry. So jump on no carry. This line will not be completely executed. So if it is completely executed, then it will take 3 machine cycles, and otherwise it will take 2 machine cycles. So here you can see it is now 9. So previously it was 7. So 2 machine cycles, it is not completely executed. So now program is jumped to this location, means there is no jumping, program comes to the next location, that is called S2, this line. Okay, so I am calling the subroutine 2 here. So okay, go to the subroutine 2. So this is my subroutine 2. So when I am calling the subroutine 2, you see, once this line is executed, this line, okay, let me start from the beginning again. Okay, so you see this done, this is done. Here now it is not executed, it is pointing to this location. So stack pointer value is here FFFF. You have not done anything related to stack pointer, you just call this subroutine. So what is the information we know? Whenever subroutine is called, the location, the address location of your next instruction will be inserted into the stack. Okay, normally these things happen internally, but in this particular environment, what is happening, you will see that a location of this instruction will be inserted into the stack. Okay, so what is the location of this instruction? 800A. So here you see that already it is inserted because I have just executed my program once. So here you see that this done. So it is inserted into the stack 800A. The upper 8 bit goes to first location FFFE, next 8 bit goes to this location. This is the lower 8 bit, this is the higher 8 bit data of your address. Okay, which address it is? Actually 800A is the address of this instruction. Call S2, this line instruction is address of 800A. Okay, so this is inserted into the stack, but you have noticed that nothing is inserted into the starting location. Why? Because this is the operation of the stack. How stack is handled? This is the stack pointer location, it will decrease by 1, data is inserted, again it will decrease by 1, the next data will be inserted, 16 bit data is inserted, completed. Okay, so for initially it is here, it will decrease by 1, a stack pointer register decrease by 1, data is inserted, sp minus 1, again data is inserted. So currently what is your top location of your stack pointer? Sorry, what is the top location of your stack memory? Not stack pointer, stack memory. This is the top location of your stack memory. So here is your stack pointer. So stack pointer value is what? FFFD. You don't do anything on this stack pointer. Microprocessor itself change the value of the stack pointer according to the operation of your stack memory. So data is inserted into the stack. You have not inserted any instruction to insert for insertion the data into stack, right? You have not used push instruction there. Okay, in this call S2, you just call this subroutine 2. You have not pushed any data. Microprocessor pushed the data. Which data? The address location of this call instruction. Okay, in this environment, it pushed this data into this call, into this stack 800A. Okay, and then it will go to that subroutine. Okay, so this is subroutine 2. So in this subroutine 2, what is the instruction written? Pop B. So pop B means what? The stack pointer will So whenever there is pop operation, so how that pop operation will be executed? So current location of your stack pointer, from that current location of your stack pointer, data will be popped out to the lower register. BC is the register pair, so data will be popped out to C. Then stack pointer will increase by 1. Then it will pop out the data in that location into higher register, that is B. So 80 will be there. So first, what is happening? It is currently stack pointer is currently FFFD. It is decreased by 1. Data is popped out. Then again it will be increased by 1. So it will be at FF location. Data is popped out to B. So after this pop operation, you will see that your stack pointer value will again changed, where it is now currently FFFF location. It is here. Why it is here? Because you have done this pop operation. So when when you are doing this pop operation from the, again I am saying, okay, just listen. So when I am doing the pop operation, here you can see FFFD. So that is the location of your stack. It is not executed. Pop instruction is not executed. It is pointing. It is not executed. Once it executed, then the stack pointer register value will change, because these two data from the location FFFD and FFFE will be popped out to where? BC register pair. That is the pop B instruction. Okay, how it will be popped out? So currently stack pointer register is FFFD. So FFFD, from that location stack pointer will increase by 1 and data will be popped out. So after first pop out data, what is the stack pointer location? FFFE. Then again it will increase by 1, data will be popped out. So then its value will be FFFF. So once this pop instruction is done, the value of stack pointer registered is FFFF. That means your top of stack location actually now FFFF. Okay. So now what you can do? You can, after this you have to return. So return is very interesting instruction. Return means what? It will return to your next instruction, that is JMP end. This instruction it will return here. So this is the subroutine of 2 lines of code. Okay, it will return to this line JMP end. So when it will return to this line, how it will return? It will return to this line by checking. Means you don't need to do anything. Microprocessor will get the data return address from the stack. Okay, so it will get its return address from the stack and it will return to this location. Okay, so you will see again the stack pointer value will change. Why it will change? Because when you are returning, microprocessor will take out the data. Understand this concept. Return means pop out operation basically. When you are when you are inserting call instruction in your program, actually you are doing a push operation. Call instruction is doing push operation because it is inserting the address into the stack memory. Return instruction is actually doing pop operation because it is taking out the data from the stack memory and putting that data into the address bus, because in that location you have to return back. Okay, so this is the pop operation. So return means pop operation. So here you have seen that whenever you call this subroutine to, the stack pointer value changed. Okay, it is initially it was FFFF, call instruction execution done, its value becomes where? FFFD, right? It is changed automatically because microprocessor will just insert this data 8008. So data will change, stack pointer register data will change. Okay, again, so in the subroutine whatever operation you can do, that is not a problem, but at the end you have to write this instruction return. So when this return instruction will be executed, again the stack pointer value will change. Okay, so when call instruction was invoked in your program, data is pushed into the stack. When return instruction is invoked in your program, data will be popped out from the stack. So when it will popped out, obviously the stack pointer value will increase, right? It is not decrease. So insertion push operation decrease the stack pointer register value. Pop instruction increase the stack pointer register value. SP becomes SP plus 2 after pop operation, right? After one pop operation, your SP becomes SP plus 2. After one push operation, your SP becomes SP minus 2 because you are inserting 16-bit data or you are taking out 16-bit data. So SP becomes SP plus 2 or SP minus 2, right? So here also in the return instruction, SP becomes SP plus 2. But what I have told you, this is the last location of address location of your 16-bit address bus. There is, I cannot go beyond that. So I cannot go beyond that means what? Actually, it means that I cannot go to the 17-bit representation of your memory address. But I can ignore that 17th bit. If I add 1 with this stack pointer, so where I will go? I will go 0000. That is the starting location of your RAM or ROM. Okay, so that will happen here. You will see your stack pointer value becomes 0001 because FP plus 2. So plus 2 means FF plus 2 means what? 0001. So you are actually coming back to the starting location of your RAM or ROM chip. Okay, so the stack pointer value is now is 0001. Okay, so why it is become 0001? Because can you see any changes in stack memory? No, you cannot see any changes in stack memory when you do the pop operation. Why? Because pop operation means you are just copying the data from this to any of the memory to memory locations and copy and doing paste operation. So in the copy paste operation, obviously the source data will not change. So you will not change, will not see any change in stack memory. Okay, but the stack pointer register value will change. Okay, so this program comes to this location, and here this is unconditional jump, so it will jump to this location. So your program will end here. Okay, so this is the operation that is related to stack and the push pop operation called jump operation, unconditional jump operation. Okay, so basically what we understand, we can use stack according to our needs. Okay, so here I have initialized the stack. If I just forget to initialize this stack, so what microprocessor will do? Microprocessor will not take this location. So it will take which location? It will take this location. You see, this is the location 0000. So what happened? Now you see the difference. What is happening? So there is carry. So this call S2 subroutine 2 will be called, and which location, which data will be inserted into the stack? Which data will be inserted into the stack? Can you tell me? It will insert 8007 into the stack. Okay, so where it is inserted this into the stack, because the first location is initial location was 0000. In that location nothing will be inserted. It will decrease by 1. SP becomes SP minus 1. So 0000 minus 1 means FFFF. It will insert the higher 8-bit data, that is 80, and it will again decrease by 1. So SP becomes SP minus 2. Finally it will insert the lower 8-bit data, that is 07, that address location. 8007 is the address location of call S2, starting location of this instruction 8007. So it will insert that data into the stack. Okay, and then it will pop out the data. So which data will be popped out? Your currently your stack pointer is FFFE. So FFFE, this from this location 07 will be popped out into the C, then 80 will be popped out into the B, right? So you see, popped out 8007 into BC, and then it is comes to this location. Okay, so after pop out there is return instruction. So again I'm just going to execute this program. I missed one thing, so here is done. call operation is done. So your program is here. So your FFFE. So pop operation is done. So once you've done the pop operation, what is the location of your stack pointer? 0000. Why? Because it is increased by 1. Pop out the first data into C. Again it will increase by 1 from this location. So your value becomes 0000. Pop out the second data into B. So this is the pop out of data, and this is the location of the stack pointer. From this location, if you again do the pop operation, because return, whenever you are invoking return instruction, it is doing the pop operation. So pop operation means it will increase the stack pointer register. Okay, you cannot see any changes into the stack memory content. It will be same. You see, it is done. Nothing is changed into the stack memory content. But what is the stack pointer value? It is increased by HP plus 2. So HP was 0000 plus 2 means 0002. You are getting HP plus 2 value into the stack pointer register, and you are coming to this jump end instruction. It is executed. Your program ends here. Okay. So this is all about the conditions when there is a carry in your program. Okay, so these things are happened if there is a carry, and if I take a value where there is no carry. Okay, so what happened, you see? So I have not changed the content of stack. Okay, suppose like this, it was there, something is there, no problem in that. It is executed, so there is no carry, so this line will be completely executed. So it jumps to this. Now subroutine 1 will be called. Which data will be inserted into the stack? The content of PC 800D. 800D. 800D is the location of this instruction 800D. Okay, so this data will be inserted into the stack. You see 800D inserted into the stack. Okay, and what is the value of your stack pointer register? FFFE. Same thing. I have not initialized the stack pointer, so by default it was taken by 0000. So it becomes FFFE once the data is inserted into the stack. Then what I am doing, initializing HL register pair. It becomes F5555. Then what I am doing, I am inserting some data into the stack. So which data I am inserting? Content of HL. So data is inserted into the stack. So you can see the changes occurs into the stack memory whenever you are inserting a data. But whenever you are pop out data from the stack, you will see no change in the stack memory. You will see only change in stack pointer register. So what is the stack pointer register after inserting the push H instruction? A55 inserted into FFFD, because previously it was at FFFE, that is the location of stack pointer. Then push H instruction instruction is executed, so it becomes SP -1. Insert the higher data, higher 8-bit data, so content of H. Then it will SP -1 again, so insert the lower 8-bit data, that is again 55, the content of L. Okay, so this is inserted. Then return instruction. Again, return instruction means pop out instruction. So I cannot see any change in stack pointer, stack memory. Sorry, I cannot see any change in stack memory, but I will see change in stack pointer register. Can you guess what will be the stack pointer register value after execution of this return instruction? It is a pop instruction, so it will increase the stack pointer value by 2. So FFFC DE, so its value becomes E. So FFFE, you cannot see any changes in stack memory because it is a pop operation, but you can see the changes in stack pointer register. So your program ends here. Okay, so this is all about this stack and call, poke, jump instructions. I hope this thing is clear to everyone. Okay, so I think I can stop my discussion here, or this is just for showing you the branch and machine control instruction for push, pop, call, jump, return instruction. There are EI, DI instructions. These are the interrupt related instructions which are normally not used in normal program. Ream, SIM, these two instructions, this is also interrupt related instruction which is not basically used to used in this current environment. Okay, So because you can see that these are the interrupts, and whenever we are talking about the interrupts, we have to connect some peripheral device with 8085. Then only we can start interrupting. So to interrupt 8085, some interrupting device should be connected with 8085, and that thing is not possible to do in this environment. So I am not going to show the operation of this instruction here. And there is there is RST. RST, what? This is also restart. This is also instruction related to interrupt, software interrupt. Remember RST 0, 1, 2, 3, 4, 5, 6, 7. So these are the software interrupts. There are total 8 software interrupts. Okay, 0 to 7. So you can insert the software interrupts in your program. Okay, this RST instruction is kind of your you can say this is kind of a call instruction. Instead of call instruction, I can use RST 0 here. Okay, so RST 0 means what? Or say RST 1. Better I use RST 1. So RST 1 means what? RST 1 means it is actually means that it will transfer the program to a particular location, which is the location of restart 1 software interrupt. And what is the location of this restart 1 RST 1 vector address? What will be the vector address? So because in case of interrupt, you know that we are talking about vector address. These are the vector interrupts, and we'll talk about we have already talked about this thing, interrupt service routine. So whenever there is an interrupt, program sequence will transfer to interrupt service routine, right? So RST1. So the same thing. RST1 or call instruction is quite same. In case of RST1, your program will transfer to which location? Interrupt service routine location of your RST1 vector interrupt. Okay. And what is the vector address? So you have to multiply 8 with this. Okay. So if you multiply 8, so it becomes 0008. So it will actually transfer your program sequence to 0008. Let me just execute this program. So this is done. Okay. So okay, so there is no carry, so program will not actually do this operation. So let me just take another data, say if. Okay, so if I execute, so I will see what change. So it will come here. Okay, so RST1, you can see what is RST1. RST1 means CF, its corresponding hex code is CF. Once is executed, so once is executed, then what happened? Once is executed, then what happened actually? So your program sequence actually goes nowhere. It starts from this because I have not written anything related to this interrupt, software interrupt. So to write a code related to software interrupt, I have to write something related to that RST instruction. Okay. So what I have to write actually in that instruction, suppose RST1, in that RST1 means which location actually it will invoke 0008. Okay, so basically here in this environment, if I want to show this operation of the instruction, it will be little difficult because there is no interrupt sources we are actually using. So better I will stop this thing here. I will discuss in the next lecture. There I will get some more data about this instruction, then I will share that thing with you. Okay, so better I just stop this talking about this RST1 here. So let me just finish my discussion over this call return push pop instruction, not any instruction related to your interrupts, because RST is also ream, sync, and EIDI, all are this kind of instruction. Better I can go for this one. Which one? Let me just go to this set of instructions. Just one second. I can go to this instruction PCHL. Okay, so PCHL, I can show what is the operation of PCHL. Suppose you have written this line of code MVIA 54. Okay, then LXI H. Say you have written the address, you have initialized the address 6666. Okay, So then you have written PCHL. Okay, so in case of PCHL, say you have written something into that location. Say I just take 6666 this location here and write some date program into these locations. Which program I will write? Say I write MVI MVI what? MVI A MVI C comma MVI C comma 76. Okay, and let me just show you one by one. So I take this data. Okay, this is the next data. So PCHL. Okay, E9. So now you see that you are actually at this location 8005 location. Okay, once you execute this line, you are now at which location? 8006 location. Okay, because you have not written anything related to that address, the 666 location. Okay, let me just write one thing into that address. Okay, so 0E and 76. So if I write this thing, I think in this environment whether it will work or not, I have to check. So what I am doing, instead of writing this thing here, I have written this code, line of code there. Okay, so let me just execute and see what is actually happening. So actually in this case, it is not actually happening the way I want to happen, because the function of PCHL is to load. You see that load the program counter with HL pair. So it will load the content of HL pair into the program counter. So if when it will load the content of HL pair into the program counter, so in the next loop, if I execute this line, this code, so program counter value should change to 6666. So in that case, if I execute the next, if I go to the next line execution, then in that 66 in that location, whatever the data I have written, that thing needs to be executed. Means I can, it is kind of a jump instruction. Jump means in if I want to jump, let's say if I want to jump, okay, JMP at which location? The location is L1, okay, and say in that location I am jumping. Okay, so and so I use in some instruction here INRC and say this is my the location, jump location. Okay, so there I can jump. So jump means say I am doing here another operation INRH. So end of this program, so HLT. Okay, so this way I can show you. So if I execute this program, so what it will do, this program, what program will do, so it will jump to this location INRH, and there it will increase the content of HL register pair, H register only. So content of H register will increase by 167, end of your program. Okay, so this thing I can do using jump instruction. I can, whether I can do this operation using your say whether this thing I can do using any other instruction like PCHL. Okay, yes, I can do it. Logically, I can do it. I don't know whether we can do it in this simulator or not, but logically, I can do this operation. To do this operation, what I need to do, I need to put this location value into the HL register pair instead of 6666. Okay, so what is the value of this location? So after before halt it is there. So the value of this location is 8008. Okay, sorry, not 800, sorry, this is a 1 byte instruction, right? So 8008, the value of this address of this INRH is 800A, right? So I can put 800A here, okay, and see what is actually happened in this particular environment. So this one is done. So PC value is 800A, you can see, and nothing is actually happened there. Okay, so PC value is now this. It is loaded with 800A content of HL registered pair, and in 800A location is in that location whether any data anything is written, no. So if I write something into that location, say in 800A I am writing this code 76. Okay, 76 means end of the program. So let me just see whether it will work or not. So it will go there. So your program sequence jump to that location. So program sequence will jump to this location 800A. Okay. So if I write this one also in INRL, okay, and then I execute. So you can see that your program sequence is jumping to that location, right? Here it is the code actually. So if you want to use PCHL, it is kind of thing that you can do like this way. PCHL, so what is PCHL? It will look actually this address 800A. So 800A, so in that 800A, what you have written 76. That's why it will executing this line of code. If I write another code, say this one INR M, okay, INR M. So what happened? Let me just execute. So PCHL program jumps to that location. So which location? 800A location. There it will get INR M. So INR M means what? In INR means this thing will be increased. So in 800A in that location, previously I have written 34 is there. So here it will become 35 and it end of your program. Okay. So according to your program, what is there in that location 8000A. So in that location actually you have written this hex code according to program 34. This thing is there. Okay. So you want to jump in that location. Okay, so you can use this instruction jump L1. Okay, but instead of using jump L1 you are using actually PCHL, so you can do it. But here what is the address of your L1 INRH? What is that address? I'm going little far here. INRH, can you tell me what is the address hex code of INRH? Let me just cross check. INRH 24. Okay, so and it is 24. Here I'm writing HLT. Okay, so your total program is taking starting location is 8000 and ending location 800B, and this INR H is at the location 24 8008. So if I write here 8008, so I can expect my program will jump to this location. Okay, yes, it is jumping to that location. So now you can understand that PCHL is something like your jump. So here I don't need to use this label. Okay. So what I am jumping PCHL, I am jumping to this location 8008, and this location actually the location of your data of your main program, right? Jump instruction. So when we are using jump instruction, remember that we are jumping from one location of your main program to another location of your main program. So which address you need to specify into the HL if you want to use a PCHL instruction, the address, any address where you want to jump in your main program, right? So like this. So if I can I write this one 8000? Huh? If I execute this code, if you see what happened, yes, I can go this direction also. I can jump this is kind of a loop I can create using this instruction. Okay. Otherwise, I can also do this operation. Okay. So I found that 8000. I want to jump to this particular line. Okay. So 8008. So 8008, it will jump to this particular line. Okay. So if I execute, this is unconditional jump. It will jump to this particular line. Okay. So before using PCHL, you need to calculate at which location you want to jump in your main program. Okay. You calculate that thing, then you use that address as a content of your HL register pair. Okay. If I want to jump to this location INR M, so what is the location? 800A. I can also jump to this location INR M 800A. Okay, so then I have to use that address into the HL register pair. Okay, so it will jump to that location. So this is our conditional jump, not conditional jump. It is PCHL is equivalent to unconditional jump. Okay, instruction. So unconditional jump instruction is quite, it can be done using PCHL instruction. Okay, that thing you can understand from this. And there are XTHL, XPHL. These are the stack, extend the top of the stack with HL register pair, copy HL register pair into stack pointer. Okay. So by this using these two instruction, you can change the stack pointer. Okay. How we can change the stack pointer? You can exchange the content of HL register pair with stack pointer register. So your stack pointer register value will change. That means it will then locate any different address. Okay. So if I take this thing, okay, okay, there are two set of locations I have taken. Okay, so say this is the one stack location, this is the another stack, second stack locations. Okay, so if I say if I initialize my stack pointer with this first location FFFF, then I initialize my HL register pair with 666B, then and say now I use push instruction, push H. Okay, so I will push the content of HL into the stack. Again I do push push B, so it will insert 00 because nothing is there in BC register. It will insert 0000 into the stack, but stack pointer register value will change. Then if I exchange the top of the stack using XTHL, exchange the top of the stack pointer is what is XTHL? Exchange the top of the stack with HL register pair. So it is not actually change the content of stack pointer register. It will change the content of top of the stack location. Okay, and SPHL, it will copy the HL register pair into the stack pointer. It will change the stack pointer register value. Okay, these two are two different things. So XTHL means I am exchanging the top of the stack location value with HL register pair. Okay, so what is the top of the stack location value here? So let me just change this thing. This is done first, then this is done second. Okay, okay, so what you will see, just execute this program. So FFFF stack pointer, then it becomes 666B HL register pair. Okay, then push B. So you are pushing what? Content of BC register pair content, that is 0000. So content of stack pointer register is FFFF. It will be decreased by 2 because this is push operation. Decreased by 2. and what you have inserted there 0000, and why you can see that some data is already in this location, because it was there inserted previous in previous operation. Okay, it is not inserted during the current in program, it is inserted in previous program. So the previous data that is not needed here in this program. Then what I am doing, I am doing again another push operation. So again, your stack pointer register value change FFFB minus 2 done, is done from FFFB minus 2. It is now FFFB. Two things is inserted. One is content of H 66, another is content of L 6B. Okay. Then I am executing this XTHL. So I am what I am doing, exchange the top of the stack value with HL register pair. So I will not see any changes. What happened? Push B. So it is pushed into the stack, then XTHL. So when you do the XTHL, when executed, exchange, you can see here, exchange the top of the stack with HL register pair. Exchange between HL register pair and top of stack. Top of stack means 6B and 66, and HL register pair is 666B. Okay, so it will be decreased. Stack pointer value will not change, FFFB. Okay, but what is happening into H is totally I don't think it is something happening in the correct way, because there should be some value at H. Okay. Hmm. So, okay, let me give some value into register LXI BC LXI B. So 4532. Okay, so execute first, second line, third line. Okay, so 4532, then push H, done, then it becomes vanished. Okay, so again I'm doing same thing, push B. Okay, so not push B, say on this. Okay, push H. What I am doing, push H means I can do the push H operation first here, so I will see any changes occurring into the stack. Okay, so here FFFF. So now first FFFF. Now this is done. So BC and HL. So push B means what? You will see that content of stack will change 66 and 68. Currently it is showing 4532. It will change 66 6B. Okay. Push B, it will again change 4532. Why? In the VC register pair you have 4532. Okay, very good. So what is your current stack pointer location, register location? FFFB. What is the content of stack? So there are 4 data inserted into the stack. Okay. XTHL. So what it will do? It will extend the top of the stack locations value with HL register pair. Okay. So L content will go to this FFFB, and FFFB content will come to the L. So 4532 66 6B, it will be exchanged. 66 6B. Okay, so I think this instruction is not actually executing in a proper way in the simulator. Or am I doing something wrong? Instead of taking this thing here, I take a different value, say 7777. Let me just execute. Okay, say I, instead of doing this operation, if I do this, so what actually happening? All this content of this. So if I this, okay, okay, very good. I just want to see at which point this instruction will work. So in this case, I just make everything 0 0 here. Okay, say this is the starting location of your stack, so I make this thing also 0 0. Okay, very good. Now I start execution of my first program 8000. So this is inserted into a BC register pair, and I inserted this data into top of the stack. One, I am executing STHL, means I am exchanging the content of the top of stack with HL register pair. So HL register pair content is 0000. So 00 is transferred, but why the content of age vanishes totally, I don't understand. So that means it is not executed properly in this environment. Stage. So I cannot explain this instruction operation. Okay, thank you, very good. So let me go to the next instruction, SPHL then. Okay, instead of this, I show you SPHL here. So in case of SPHL, what happens? So stack pointer, in case of SPHL, I can actually move my stack into a different location. Okay, where say 666B, 666B, this is the location. Okay, so here I can, there are two stack locations. There are two stack you can see here. So one stack location start from stack pointer here. Another stack location I can start from this location. How? Using SPHL. Okay, so for that reason, what I need to do, I have to initialize my stack pointer this. Then this is the HL register pair content. That is the address of the next stack location, and then I can initialize BC register pair and push that data into the normal stack. Okay, then I exchange, then I use SPHL. SPHL means what? Copy HL register to stack pointer. So stack pointer value will change. It will be changed to 666B, and there if I insert and again push B, then I can insert the data into a new stack. Okay, so this is what actually I means here. So you see that what is pushed into the stack, 4532. SPHL executed, stack pointer value will change 666B. Okay, if you insert, where it will be inserted, in these two locations. Okay, so this is the push B instruction. Okay, got it. So this is SPHL instruction. Here I have shown you how we can use two different stack memories. One stack memory, stack 1, another stack memory, stack 2, in a single same program. There, if I want to swap between these two, then I have to do this way. I have to use my instruction SPHL in this particular way. Okay, so it will actually insert, it actually give you this thing. Okay, push B means it will now work into the stack pointer 2. How you will go back to stack pointer 1? So in that case, what you have to do, if you want to go back to the stack pointer 1, so you have to remember that what operation you have done. So there is no actually a way you can go back stack pointer directly. Okay, like how you can jump from stack 1 to stack 2 is possible by SPHL. There is no such way you can go back to the stack pointer, stack 1 actually. Okay, because if I use SPHL, if I change the value of HL, now I can change it again LXI 8, but which value I will specify, whether I have to specify FFFF, I can do this one. So in that case, whatever the data is present in the stack 1 will be again overwritten. Okay, again it will be overwritten. Otherwise I have to remember the location of stack pointer where the operation, my last operation done in stack 1. Okay, that is the location FFFD. So if I do this one, then if I can initialize FFFD there, so after initializing FFFD there, I can use this instruction push H. So I will see that my data will not be overwritten. You see here, you jump from stack 1 to stack 2. Again you are jump from stack 2 to stack 1. There you are inserting these two data. Oh, sorry, I have not jumped it yet. Sorry. So here I have to jump again. It's PHL. Okay, so I jumped again. So and I pushed. So you see, 4532 was there initially. Then it is FFFD. Okay, but I have to remember this address. Okay, or somehow I have to store that address into a register, any other register pair. So after this push operation, I can use the instruction, like which instruction can I use to store the location of stack pointer into a register pair, into a register pair. Is it possible to get the stack pointer value into some register pair, current location of your stack pointer value into some register pair? Can you do it? Can I do it using this? No. Can I do it using this? No, exchange will not work here. LXI, it is used to initialize. It is not used to read the content of stack pointer. Okay. So if I want to read the content of stack pointer, which instruction can I use? Hmm? I can use that instruction in not in direct way. What is coming in my mind? Okay. I don't know, means if I want to read the content of current location of stack pointer, I can use XTHL, right? Because it will read the content of stack point top of the stack location into HL register pair. Okay, so I can use XTHL here, but I don't know whether it will work or not. XTHL. Okay, no DAD is actually required. Okay, let me see what actually happens here. So this done, push B is done, XTHL. So yeah, 666B. Okay, 666B. Okay, no, I cannot use here this thing. Okay, why I cannot use here? Because if I use XTHL, then again use SPHL, then both way I am using the this thing. Okay, so what I can do, I need to stop this execution here, and I can get the data whatever they are in HL register pair into some other register pair. Say MOV, which pair I am not using, DE. So move DH MOV uh, EL. Okay, so if I use these things, then I hope that I will get the data. So push B. So once push B instruction operated, FFFD is the current location. So that location I want into my HL register pair. No, I'm not getting. So what I am getting? 32. Okay, let me see what actually happens here. So nothing is going into from H to D, and 32 is going here. Okay. So here it is done. So in that case, FFFD, I know that, but I don't want to use this instruction. What I want to use here, yes, basically this operation is not actually happened correctly because XTHL is not working in this environment. I don't know why, but if I do it using STHL, then I can easily get the data of current low stack pointer location into HL, and then I can easily do the read the data of stack pointer location and save it into D register pair. Again, get back the data into HL again and do the next operation. Okay, so these things cannot be shown here, but that I hope you understand the logic. means what actually I want to do here. I just want to read the top of stack location into HL, and I save that data into D register pair. Then again, once I get the data into HL into D register pair, my this data is changed. Okay, so I should write this thing here. Okay, so I'm initializing again my HL register pair to the new location of your stack pointer. Instead of writing initializing stack pointer, I can do this. Then I can use SPHL here. Okay, so now your new stack pointer value will be 6b. Data will be inserted there. Push B. Okay, then after push B, again before using again SPHL, you have to get back the data from D register pair to HL. So MOV H from D, MOV E from L. Okay, so once I get the data here, then I can again use SPHL. Now this SPHL actually returns to the stack one. Okay, you have the data of stack one location, so you will come back to stack one. So this is the way you can operate once two stack in a same program. But I cannot say that why this XTHL instruction is not working in this environment. But if it works in this way, you can do it. Otherwise, without this, you can also do it using DAD instruction, DAD SP. Okay, DAD with SP. So initial value of your HL register pair is 00. Okay, so here you see initial value of your register HL register pair is 00. So once you do the add operation, you get the stack pointer location into HL register pair. You save that value into DE. Okay, then you go to the next set of data. There you change the value. Again, you get back. You see that the stack pointer is changed to stack address of the next stack location 6669. Again, you are getting back the data into HL. So HL is here, so it will change. Okay, when it will change, you can again go back to your stack one. Okay, so there you can insert your new data into that stack. Push H. So what value it will push? FFFD. Okay, so this way you can also do without using XTHL. Same operation. Okay, so you can do this way. I hope this thing is clear. Okay, so and there is NOP and halt. These are the normal operation, machine control, no operation and halt. So everything is I have covered this branch and machine control group. I hope this makes it clear the concept. If you have any doubt, you can mail me your doubt or WhatsApp me. Thank you very much.